We are done up to 3.4, so let's move on to 3.5, complex numbers. What is a complex number? Well, let's begin with a motivational example as we see over here. X squared plus 4 is equal to 0, consequently x squared is equal to negative 4. But here's a problem. There is no such real number x. As a matter of fact, there's no real number whose square is a negative number. Positive times positive is of course positive. Negative times negative is also positive. So we can't get negative number by squaring a same number, multiplying the same thing twice. The lowest I can get is 0 because 0 times 0 is 0. So if it is necessary to get x squared is a negative number, then what do we do? Well, we have to go outside the real number system, and this is how you do. First, we start with defining a new number, which we call an imaginary number I, such that I squared is equal to negative 1. And then we take a couple of real numbers, a and b, so that we write a plus bi, and that is called a complex number. So one complex number, a plus bi, corresponds to a pair of real numbers, a and b, or a comma b. A complex number system is actually two-dimensional in that regard. Here in a plus bi, the a is called the real part of this complex number, and b is called the imaginary part. Both a and b are real, so even though this term says imaginary part, b is not imaginary. It's a real number. Imaginary part of a complex number is a real number actually, same as real part. And then, of course, you have to remember I squared is equal to negative 1. Just regard I as a character and you can do all kind of algebra, but at the end, just remember, whenever I squared show up, replace it by negative 1, and then you can do all kind of computations about complex number system. Okay, let's resume that in my notebook here because our textbook tends to be a bit too verbose. And let's begin with some examples here. 2 plus I, okay, a real part is 2, imaginary part is 1. And here's another example, 3/5 minus 4/5 I. And here's the third example, negative 3 plus 2i. Those kind of things are complex numbers, a plus bi form. Now, did I say the complex number system is two-dimensional? Well, here it is. A complex number is given by x plus yi, and x is, well, a number, a real number that can be selected anywhere in the real line, and same goes to y. So it corresponds to x comma y in rectangular coordinate plane. That coordinate plane is called complex plane, and x plus yi corresponds to x comma y. We have these three examples here, and let's plot them. Okay, here they are. 2 plus I is the right-hand side dot. It corresponds to 2 comma 1. And the second point, 3/5 minus 4/5 I is the middle dot, or the one down below. It corresponds to 3/5 comma negative 4/5. And then top left-hand side corner dot corresponds to negative 3 plus 2i, or in coordinate, negative 3 comma 2. So what's the moral of this story? X plus yi corresponds to x comma y in rectangular coordinate plane. So every complex number corresponds to a point in a coordinate plane, which we call complex plane. Now, this complex plane and this coordinate plane, or this kind of correspondence, helps us to consider complex numbers as well. Consider complex number as visual quantity, or, oh yes, that's a better term. helps us visualize the complex numbers. So just like real line helps us visualize real number system in a line, complex plane helps us visualize complex number system. Now that we can see complex numbers, let's define some more quantities. One such quantity is modulus or absolute value. They're the same thing. It is defined as square root of x squared plus y squared. Basically, this is a distance from the origin. So for example, if we have excuse me, if you have a 2 plus I, then we can calculate its absolute value or modulus by x squared plus y squared, square root of x squared plus y squared, in short like this. Square root of 2 squared plus 1 squared, and we have square root of 3. And that is the distance to this point from the origin. How about the next example? What is the modulus of this one? Square root of 3/5 squared plus 4/5 squared. And here it is. We're going to have 1. I designed it that way. How about the third example, which is top left-hand side dot in this plot. And what is the absolute value or the modulus? Square root of 3 squared plus 2 squared. Square root of 3 squared plus 2 squared, which is square root of 13. We can calculate absolute value of a complex number simply by this formula, square root of x squared plus y squared, algebraically. And geometrically, what does it mean? It means the distance from the origin. Unlike real number system, there's no way to determine which complex number is larger and which is smaller. However, it is possible to tell which one is farther away from the origin, which one is closer. And what we need to do is to take the absolute value, the modulus. Next quantity I have to talk about is something called conjugate. X plus yi becomes x minus yi. That's conjugate. So simply change the sign of the imaginary part and we have conjugate. Well, we have 3 complex numbers here, so let's find out their conjugates. 2 plus I, well, we have to change this middle sign, right? So complex conjugate will be 2 minus I. By the way, the notation for complex conjugate is z bar. So z bar is 2 minus I. This plus becomes minus. That's about it. How about this example here? 3/5 minus 4/5 I. All I have to do is change the middle sign. That's how you get conjugate. So 3/5 plus 4/5 I. That's my complex conjugate. Let's see. Let's look at the pictures. These are original 3 points, and then let me show you conjugate. Let's see, this 2 plus I will become 2 minus I, so it's going to correspond to 2 comma negative 1. 3/5 minus 4/5 I will become 3/5 plus 4/5 I if you take conjugate. So we have sign change in second coordinate. Likewise, we have these. And you're looking at pictures of those conjugates. Let's plot those together in same viewing window. And here we go. Excuse me. Okay, now here we go. Do you see some symmetry here? X plus yi, each is going over to x minus yi. So y coordinate change sign. That's basically what happened. The blue is the original, and then red is the conjugate. And then please note that blue and red are symmetric with respect to the x-axis. That's because we simply changed the sign of the y-coordinate. That's what complex conjugate do. And that if you measure the distance from the origin, well, it stays the same because x squared plus y squared, or square root of x squared plus y squared, will not change if I change the sign of y, because we're going to square it and make everything positive anyway. So those are complex planes, modulus, and then complex conjugate. Excuse me just a moment. I have to get rid of these pictures before moving on to the next example here. Okay, now that we talked about those geometry, let's talk about some algebra here. Plot the given complex number in a complex plane, and then find its complex conjugate and plot it, blah, blah, blah. Okay, let's go ahead and do that. Once we have x plus yi form, then we can plot it. Before that, it's impossible, or it's very difficult. So how do I work out this kind of complex number? Well, algebraically work it out. Just FOIL it, and just remember, whenever you have I squared, that's going to be replaced by -1. And here's the solution. 3 plus I times 4i plus 1, just FOIL it, and then we get 4i squared when we do inside. And then I squared is -1, so 4i squared will become -4. After simplification, like terms together, we get -1 plus 13i. And once we have that, we can find out its absolute value by taking 1 squared plus 13 squared and things like that. And if we want to plot it, yes, you can plot it. It's going to be plotted to -1 comma 13. I didn't bother plotting it in this notebook, but in a graphic paper you can easily do that. This is going to be x coordinate, and that's going to be the y coordinate, -1 comma -13. Something is not right. What did I do? This should be conjugate. I apologize. Yeah, that should be conjugate, because this plus 13 became -13, so some change took place, as it should. So z is -1 plus 13i, so it should be, you should plot it at -1 comma 13. How about the next example? It's pretty much the same. Just use algebraic manipulation. You can use either complete square or FOIL it. It doesn't matter which way you do. But just remember, whenever you encounter I squared, it'll become -1. Here I ended up using complete square formula. So okay, 4 minus 12i plus 9i squared. But I squared is equivalent to -1. So 9i squared becomes -9. So we have simplification. What we have in the end, we have -5 minus 12i. Oops. So if I want to plot it, I have to plot it at -5 comma -12. Conjugate, easy. All I have to do is change the sign of the imaginary part. And then modulus, well, that's equally as easy. 5 squared plus 12 squared, and then add them up and take the square root. Happens to be we have square root of 169, or square root of 13. Somehow I did not align them very well. Okay, that looks good. Now, what if we have a fraction? Well, that's more interesting, but looks like we'll have to do that in the next video. We're going to talk about how to deal with division, and that is related to conjugate big time.